Hey folks, and today we're going to discuss the concept of duality in linear algebra. I assume that you are familiar with basic concepts of linear algebra like vector spaces, linear dependence/independence and bases, linear maps, matrices, and lastly quotient spaces. In this video, all vector spaces are assumed to be finite dimensional. With that out of the way, we may proceed. The notation we'll use throughout this video will be LV semicolon W will denote the space of all linear maps of the form phi from V to W endowed with the vector space structure. Consequently, LV will denote the space of all linear forms on V. First, we'll take a look at the definition of a bilinear form. Let V and W be vector spaces over the same field F. Then phi from V cross W to F is a bilinear form if and only if for all V1, V2 in V, W1, W2 in W, and scalars lambda mu, phi satisfies being linear in both arguments. Another thing to notice is that given fixed vectors v and w from v and w respectively, we have induced linear forms on both vector spaces defined as phi sub v, which is just fixing the second argument as w and treating it as a linear form, and phi sub w, which is just fixing the first argument as v and treating it as a linear form. In addition to that, we say that phi is non-degenerate if and only if given a vector v in big V such that for all w in big W we have phi of v comma w equal to 0. That implies that v itself is equal to 0. And given a vector w in big W such that for all vectors v in big V, phi of v comma w is equal to 0, that implies that w itself is equal to 0. Now finally we can define the concept of a dual space. Given a vector space V over the field F, a vector space V star over the same field, both equipped with a non-degenerate bilinear form, typically denoted with angle brackets, are called a dual pairing. V star is said to be dual to V, and its elements, typically denoted as V star, are called covectors. And the bilinear form is called a scalar product on V and V star. Note how this definition is symmetric. So given such bilinear form, we can construct another bilinear form defined as just swapping the V and V star, and under it, V is dual to V star. Now let's look at some examples. For field F, taking V star and V to be equal to the field, and defining the scalar product for some lambda and mu as just their multiplication. By basic properties of fields, we can show that this form is non-degenerate and bilinear, thus a dual pairing. And here we say V is self-dual because V star is equal to V. Another example is to take F to be the real numbers and vector spaces to be R3 with a scalar product defined as the typical inner product on R3. So just multiply the components and add them up. It easily can be shown that this is a bilinear form and it is non-degenerate. As a hint, use the standard basis of R3. And lastly, one of the most important cases of duality is for any vector space V over field F, take V star to be the space of all linear forms on V and define the scalar product as just applying F to V. It's not all clear that this will be a non-degenerate bilinear form, so let's show it. So take F to be a linear form such that for all vectors, F applied to V is equal to 0. By definition, this is a zero map, so we are done. For the second argument, we want to show that given a vector v, such that for all linear forms, f applied to v is equal to 0, that implies that v itself is 0. Taking the contrapositive of the statement, we get that given that v is not equal to 0, that implies that there exists a linear form such that f applied to v is not 0. So let's construct such map. Consider v is non-zero. Obviously, then the set with only v is a linearly independent set. Thus, by basis extension theorem, we can extend this set to be a basis for all the space v, and defining f at v to be equal to 1 and f at the other basis vectors as 0. By unique extension theorem, we can extend f by linearity, and by definition, f at v is equal to 1, which is not 0, thus such map exists, and we are done. So taking v to be v and v star to be the space of all linear forms on v with the scalar product is a dual pairing. And in fact, The last example is the most universal dual pairing, because as mentioned above, given a dual pairing V star with the scalar product denoted with angle brackets, any V star constitutes a linear form, which is just fixing the first argument as V star and treating it as a linear form. Thus, naturally, we defined big phi, which is the map from V star to the linear forms on V, as sending V star to the corresponding linear form. By bilinearity of the scalar product, we have this map being linear, and by non-degeneracy, it's in fact injective. To show that it's injective, take V1 star and V2 star such that phi of V1 star is equal to phi of V2 star. So for all vectors, we have V1 star scalar product with V is equal to V2 star scalar product with V. That implies for all vectors we have V1 star minus V2 star scalar product with V is equal to 0. So by non-degeneracy we have that V1 star minus V2 star is equal to 0. So in fact V1 star is equal to V2 star, and we are done. By symmetry we have a linear injection phi prime from V into the space of all linear forms on V star, and using that the dimension of space of all linear forms on V is just equal to the dimension of V, we deduce by rank nullity theorem an inequality z dimension of V star, which is equal to the sum of the dimensions of image of phi and kernel of phi, which is by injectivity is equal to the dimension of image of phi, which is less than or equal to the dimension of the whole space it maps into, which is just the dimension of V. And symmetrically we get that the dimension of V is less than or equal to the dimension of V star. So putting it all together, we have the fundamental theorem of dual pairings. Given a dual pairing, V star with a scalar product denoted by angle brackets, then dimension of V is equal to the dimension of V star. And returning to the universality of the pairing V equal V and V star V equal to the space of all linear forms on V, we get as a corollary, given a dual pairing V star with a scalar product denoted with angle brackets, then V star is isomorphic to the space of all linear forms on V, and symmetrically V is isomorphic to the space of all linear forms on V star, with a natural isomorphism phi from V star to the space of all linear forms on V, defined as sending V star to the corresponding linear form. This can be shown easily just by equating the dimensions and getting that the image of phi is equal to the whole space of the linear forms on V, so phi is surjective, so all in all it's a bijection. Thus, given two dual spaces to V1 star and V2 star, we have that V1 star is isomorphic to V2 star, and in fact, considering the inverse of the natural isomorphism between V2 star and del V, we get that for some vector V1 star, applying that inverse to the induced form by V1 star, we get some other vector V2 star from V2 star, and defining small phi from V1 star to V2 star as that vector, and applying the natural isomorphism to both sides, gets that the induced form by V1 star is equal to the induced form by small phi of V1 star. Clearly, by non-degeneracy of the scalar product and the natural isomorphism being a bijection, we have that small phi is injective, and by rank nullity theorem we have that it's surjective. Thus, small phi is an isomorphism, and in fact a unique one that would preserve the scalar product. To show that, suppose that we have two isomorphisms phi1 and phi2 from v1 star to v2 star, so that for all vectors phi v star, we have that they preserve the scalar product. So for all vectors, we have phi1 minus phi2 applied to v star, scalar product v is equal to 0. By non-degeneracy, we get that for all vectors v star, we have that phi1 minus phi2 applied to v star is equal to 0. So for all vectors v star, we have phi1 applied to v star is equal to phi2 applied to v star, so that implies that these two maps are equal and we are done. Now we can talk about dual bases. Given a basis B for the space V, then there is a corresponding basis of linear forms we call B prime, such that in the dual pairing V star equal to the space of all linear forms on V, we have that e to the I scalar product e sub j is equal to the delta ij, where the delta is the Kronecker delta. And considering the natural isomorphism from V star to the space of all linear forms on V, we have a new basis defined as the preimage of B prime, and by definition we have that the scalar product of I star and Ej is equal to delta Ij. From now on we will call this basis B star. And in fact, such a basis will be a unique one because given two distinct dual bases, we have that ei star minus ei star prime scalar product ej is equal to 0. So in fact, for all vectors, ei star minus ei star prime scalar product v will be equal to 0. So by non-degeneracy, we get that ei star minus ei star prime is equal to 0, which implies that ei star is in fact equal to ei star prime. Now returning for a second to bilinear forms, given a bilinear form phi from v times w to f, we have the corresponding subspaces n sub v and n sub w formed by all vectors such that for all w, v comma w is equal to 0, and the same is for n sub w. Now, similarly to the first isomorphism theorem, we can define phi prime from v quotient n sub v times w quotient n sub w to f as follows, and clearly it's well defined by the following argument. Now, it's also non-degenerate. So take the coset v prime such that for all cosets w we have phi prime coset v prime, comma coset w is equal to 0. That implies for all w we have phi v prime, comma w is equal to 0. That implies that v prime is in the null space n sub v, and that implies that v prime represents the zero coset. Similar argument holds for the second argument of v prime. Now returning to dual spaces. Given a dual pairing VV star, we call a pair of vectors VV star orthogonal if and only if their scalar product is 0. Given as a subspace U of V, we define the orthogonal complement of U as all vectors in V star such that they are orthogonal to the whole subspace U, and symmetrically for a subspace U star from V star, we define its orthogonal complement as all vectors in V such that they are orthogonal to the whole subspace U star. Now for subspace U, we may restrict the second argument of the scalar product to be vectors in U, and then by definition we get that the null space of V star is equal to the orthogonal complement of U, and the null space of U is equal to 0 by non-degeneracy, thus taking the induced map from V star quotient U complement times U to F gives us a non-degenerate bilinear form, so we have a dual pairing between V star quotient U complement and U, and by fundamental theorem on dual pairings we get that the dimension of U is equal to the dimension of V star quotient U complement, which is just equal to the dimension of V star minus the dimension of U complement, and that implies that the dimension of U plus the dimension of U complement is equal to the dimension of V, and symmetrically for a subspace U star of V star we get that the dimension of U star plus the dimension of U star complement is equal to the dimension of V star, which is itself equal to the dimension of V. Naturally, we identify U double complement as complement of U complement, which will be a subspace of V, and given a vector U, and remembering the definitions, you can imply that U is in fact in U double complement, which implies that U is a subspace of U double complement. Playing with the dimension gets us that the dimension of U is equal to the dimension of U double complement, which implies that these two spaces are equal. So the double orthogonal subspace is just the original subspace. In fact, this generalizes for a dual pairing V star. Given a dual pairing between V star and V double star, we call V double star the bidual of V. By fundamental theorem of dual pairings, we get that dimension of V, which is equal to the dimension of V star, will be equal to the dimension of V double star. Thus, V is isomorphic to V double star. But even a stronger statement is that there's a natural isomorphism between these. Define kappa from V to V double star such that for all V star and V star we have the scalar product of kappa V, comma V star is equal to the scalar product of V star and V. By non-degeneracy, kappa is well defined, linear, and is injective by the following argument. And again, the dimension of V double star is equal to the dimension of V, which is by rank nullity theorem equal to the dimension of kernel of kappa plus the dimension of image of kappa, which will be equal by injectivity to the dimension of image of kappa. Thus, image of kappa is equal to the whole space V double star, thus kappa is a bijection. The definition of kappa reflects the concrete case where we take V double star to be the space of all linear forms on the space of all linear forms on V, and V star to be the space of all linear forms on V, where we can identify any vector V with a map evaluation at V that sends every linear form to the scalar f of V. Thus we define kappa from V to V star assigning that vector to the corresponding evaluation map to get the following. Thus, talking about the bidual of a thing is the same as talking about the thing itself. Returning to the orthogonal complements, given any two subspace U and W of V, then U complement intersection W complement is equal to the space U plus W complement. Given a vector star from U complement intersection W complement, for all U and W we have V star scalar product U and V star scalar product W is equal to 0, which implies if and only if for all vectors U plus W we have V star scalar product U plus W is equal to V star scalar product U plus V star scalar product W, which is just equal to 0. So that's if and only if V star is in U plus W complement, which implies that U complement intersection W complement is equal to the space U plus W complement. And similarly, we can show that U complement plus W complement is equal to U intersection W complement. Given the vector U star plus W star in U complement plus W complement, for all V in U intersection W, we have U star plus W star scalar product V is equal to U star scalar product V plus W star scalar product V, which will be equal to 0. That implies that U star plus W star is in U intersection V complement. That implies that U complement plus W complement is a subspace of U intersection W complement. Now equating the dimensions of U complement plus W complement and U intersection W complement using the formulas we mentioned so far, we get that U complement plus W complement and U intersection W complement are equal. These identities are very similar to those of the Morgan laws for sets, which say A union B complement is equal to A complement intersection B complement, and A intersection B complement is equal to A complement union B complement. In fact, these are the case of duality for sets where complement of A complement, is the dual of A. But these reflect more on the duality of subspaces U plus W and U intersection W. Abstractly defined, U plus W is a minimal subspace to contain both U and W, and U intersection W is abstractly defined as maximal subspace that's contained in both U and W. So the duality is reversed inclusions, and maximality is swapped with minimality, so mirrored images of each other. Speaking of reversed inclusions, for two subspaces, U subspace of W subspace of V, we have W complement is a subspace of U complement, shown by the following argument. Now that we have talked about subspaces, we are ready to talk about linear maps. Given a pair of dual pairings VV star and WW star and linear map phi from V to W, we define V star to be dual to phi if and only if for all vectors V and W star we have phi star of W star scalar product V is equal to the scalar product of W star and phi of V. If such map exists, then it's unique. Suppose that we have phi1 star and phi2 star being dual to phi, then we have that for all vectors V and W star, we have phi1 star minus phi2 star of W star, scalar product V is equal to 0. So by non-degeneracy, we can imply that for all W star, we have phi1 star minus phi2 star of W star is equal to 0. That implies for all W star, we have phi1 star of W star equal to phi2 star of W star. That implies that these two maps are equal. And in fact, such map does exist. By taking the natural isomorphism phi sub V from V star to the space of all linear forms in V and phi sub W from W star to the space of all linear forms in W, we have that phi star of W star is just phi sub V inverse of the form induced by phi star of W star, which is just phi sub V inverse of the form induced by W star composed with phi. From now on, I will refer to interchanging the phi and phi star in the scalar product as moving phi to the left or to the right. Now let's look at some examples. An obvious first example would be the identity from V to V, and using the scalar product we get identity star of V star scalar product V is just equal to V star scalar product the identity of V, which is just equal to V star scalar product V. And by non-degeneracy we thus obtain the identity star of V star is equal to V star, which is just the identity on the vector space V star. Another very important example would be, given a subspace U of V, then we have a dual pairing U, V star quotient U complement, Then considering the canonical injection from U into V and using the scalar product, we would get that I star, which goes from V star to V star quotient U complement. For all U star, we have the scalar product of the coset U star and U, which is equal to the scalar product of U star and U, which is itself equal to the scalar product of U star and I of U, and moving I to the left, we get that it is equal to the I star of U star scalar product U. By non-degeneracy, we thus obtain that I star is equal to P, where P is the canonical projection. Now, given any pair of dual pairings V star and W star and two maps phi and psi from V to W, we have phi plus psi star is equal to phi star plus psi star, and lambda phi star is equal to lambda phi star, where lambda is just some scalar. To show this, take lambda and mu to be scalars, then we have lambda phi plus mu psi star of W star scalar product V is just equal to W star scalar product lambda phi plus mu psi of V. By linearity, we get that this is equal to lambda times phi star of W star scalar product V plus mu times psi star of W star scalar product V. And combining by linearity, we get that this is equal to lambda phi star of W star plus mu psi star of W star scalar product V. And by non-degeneracy, we thus have lambda phi plus mu psi star is equal to lambda phi star plus mu psi star. And for composition of two mappings phi from V to W and psi from W to U, we have psi composed with phi star is equal to phi star composed with psi star. To show this, take two maps phi and psi, then psi composed with phi star of W star scalar product V is equal to W star scalar product psi composed with phi of V. Moving first psi to the left and then phi to the left, and by non-degeneracy we get that psi composed with phi star is equal to phi star composed with psi star. So given an invertible mapping phi from V to W, with these relations we obtain that phi inverse star is equal to phi star inverse. By everything seen so far, we get that the map star from category of vector spaces over F to the category of vector spaces over F, sending each vector space V to its corresponding space of all linear forms on V, is a contravariant functor in the category of vector spaces over F, so it reverses arrow directions, shown here more concretely with diagrams. Or an even better way to think about this is that the star functor is a covariant functor between the category of vector spaces over F and the opposite category of vector spaces over F. So what about bidual maps? Naturally, we define them as follows. Given the bidual spaces V double star and W double star and a linear map phi from V to W, we define phi double star to be bidual to phi if and only if for all W star and V double star we have phi double star or phi double star scalar product W star is equal to V double star scalar product phi star of W star. And again, we have that such map exists and it is unique by almost the same arguments as for dual maps. Now, given the natural isomorphisms kappa sub V from V to V double star and kappa sub W from W to W double star, then we have phi double star of kappa sub V of V scalar product W star is equal to the definition of the bidual to kappa sub V of V scalar product phi star of W star, which is equal to by definition of kappa sub V to phi star of W star scalar product V, which is by definition of the dual is equal to W star scalar product phi of V, which is by definition of kappa sub W is equal to kappa sub W of phi of V scalar product W star. And by non-degeneracy, we thus get phi double star composed with kappa sub V is equal to kappa sub W composed with phi. Or in other words, the following diagram commutes. Similar relations as those for dual mappings also hold for bidual mappings. So we have phi plus psi double star is equal to phi double star plus psi double star. Lambda phi double star is equal to lambda phi double star. And lastly, we have phi composed with psi double star is equal to phi double star composed with psi double star. Only difference to note is that it doesn't reverse composition, so the map dual star from category of vector spaces over F to the category of vector spaces over F, which sends every V to its corresponding bidual space, would be a covariant functor in the category of vector spaces over F. And by bow, you may interpret the family of morphisms kappa sub V for every vector space V in the category of vector spaces over F as a natural transformation from the identity functor on the category of vector spaces over F to the double star functor. Thus, bidual vector space is truly the original vector space from the categorical viewpoint. Now, returning to the dual maps, one of the deepest things about them is that the image of phi star is equal to the kernel of phi complement, and kernel of phi star is equal to the image of phi complement. So you can say they mirror each other's fundamental subspaces. To show this, take W star from the kernel of V star, then for all phi of V from the image of phi, we have the scalar product of W star and phi of V is equal to the scalar product of V star of W star with V, which is itself equal to the scalar product of 0 with V, which is just 0. So that implies that W star is in the image of phi complement, and that implies that kernel of phi star is a subspace of image of phi complement. Conversely, given W star from the image of phi complement, we have for all vectors v, 0 being equal to the scalar product of W star with phi of V, which is itself equal to the scalar product of phi star of W star with V. That implies by non-degeneracy that phi star of W star is equal to 0, so W star is in the kernel of phi star, and that implies that these two subspaces are equal. Now we may show the first proposition. So take phi star of W star, then for all V in the kernel of phi we have phi star of W star, scalar product V, is equal to the scalar product of W star with phi of V, and because V is in the kernel of phi, we have this being equal to the scalar product of W star with 0, which is just 0. So that implies that phi star of W star is in the kernel of phi complement, and that implies that image of phi star is a subspace of kernel of phi complement. Now playing with the dimensions, we get that the dimension of kernel of phi star is equal to the dimension of image of phi complement, which is itself equal to the dimension of W minus the dimension of image of phi, and substituting the dimension of W for the dimension of W star, we get that this is equal to the dimension of W star minus the dimension of image of phi, and using the rank nullity theorem, we get that this is equal to the dimension of kernel of phi star plus the dimension of image of phi star minus the dimension of image of phi, and cancelling the dimension of kernel of phi star on both sides and moving the dimension of image of phi to the left, we get that the dimension of image of phi is equal to the dimension of image of phi star. Now applying the rank nullity theorem again, we get the dimension of V is equal to the dimension of kernel of phi plus the dimension of image of phi. So that implies that the dimension of kernel of phi complement is equal to the dimension of image of phi, but that is equal to the dimension of image of phi star. So that implies that the image of phi star is equal to the kernel of phi complement. Now in the proof above, very briefly, we also have shown that the dimension of image of phi is equal to the dimension of image of phi star. We may also do the same for the kernel. So the dimension of A minus the dimension of kernel of phi star is equal to the dimension of kernel of phi star complement, which is equal to the dimension of image of phi, and by rank nullity theorem, this is equal to the dimension of V minus the dimension of kernel of phi. So cancelling the dimension of V on both sides and negating, we get the dimension of kernel of phi star is equal to the dimension of kernel of phi. And to really contrast the duality of subspaces and quotient spaces, consider a linear map phi from V to W and a pair of subspaces U of V and S of W such that phi of U is a subspace of S. Thus we get the restriction map from U to S, which is the following injections: iota sub U from U to V and iota sub S from S to W makes the following diagram commute. Then given dual spaces V star and W star, as seen above, we have an induced scalar product on U V star quotient U complement and S W star quotient S complement. Thus the dual of the restrictions that goes from U to S would go from W star quotient S complement to V star quotient U complement. But this is even easier to see these diagrams in the intuition that the functor star from category of vector spaces over F to the category of vector spaces over F reverses the arrows as seen in these diagrams. As we have seen so far, phi and phi star have a lot in common, and the only stuff we have shown, like the rank and the nullity, only scratch the surface of how much they have in common, because intuitively they are just mirror images of each other. Lastly, we'll cover the underlying matrices. We'll just cover everything about the matrix representations without dwelling into the details. So given basis B sub v and B sub w for the respective spaces v and w, and a linear map phi from v to w, then apply phi to each basis vector v sub I and expand them in the basis b sub w to get the coefficients a sub ij, and we call this coefficient the matrix representation of phi in the basis b sub v and b sub w, and denote it as m of phi of b sub v and b sub w. Now, given the dual spaces v star and w star, we may consider the corresponding dual bases b sub v star and b sub w star, then expanding phi star in this basis and calling the matrix representation coefficients of phi star as a sub ij prime. Now, doing the scalar product of phi star of wi star with v sub j, we get that this is equal to the coefficients a sub ij prime, but also moving phi to the right and expanding, we get that this is equal to the coefficients a sub ji. In fact, this operation on matrices of reversing indices is so common it is given a name, the transpose of A, and is denoted as A to the t. So writing it down, you have the matrix representation of phi star in the basis b sub w star and b sub v star is equal to the matrix representation of phi in the basis b sub v and b sub w transpose. Now, using this fact, we can establish the property that given two matrices A and B, being the representations of some maps phi and psi, we get that A B transpose is equal to B transpose times A transpose. That's it. Now you have seen almost everything there is to duality and how mathematicians have learned to mirror stuff. Thanks for watching and peace out.